All right, so imaginary numbers, really what we need to get out of this part here is that we defined what an imaginary number was as being I. The square root of -1 is I. So we have imaginary numbers, and just that idea that we talked about a little bit yesterday, but there's a different way to think about it. That if I say, hey, what's the square root of -9? One of the properties of radicals is that we can pull it apart and say, well, that's equal to the square root of -1 times the square root of 9. And we know what the square root of 9 is. Well, that's 3, and then we've just defined the square root of -1 as being I. So I times 3, which we would just write 3I since we have that rule of letters should go after numbers, right? So just kind of think about it that way if you need to. And so what I ask you guys is, well, if I is equal to the square root of -1, then what is I squared equal to? So why is it -1, Maddie?
Because you multiply one, -1, and -1 together.
To get -1?
Oh. Well, then I don't know.
Why would it be 1, Riley?
Um, because -1 times -1 would be a positive one.
Why are you taking -1 times -1?
Oh wait, no, I don't know.
What if I asked you guys this? If 5 is equal to the square root of 25, then 5 squared must be what? If 5 is equal to the square root of 25, then 5 squared must be what? 25, right? So how can we apply that thinking if this equals that, right? Then how can we apply this thinking to this question? What did we do to the 5? We squared it. What happened to this when we did that? The radical went away. So what would I squared be equal to? Yeah, it is -1. You're right, Maddie. You just didn't know how to explain it. Okay. You said you take -1 times -1. You're not taking -1 times -1. You're taking the square root of -1 times the square root of -1. Right? When you take a square root times itself, we're left with that number that was underneath. Right? The square root of 5 times the square root of 5 is 5. Right? The square root of -1 times the square root of -1 is -1. Right? Squaring a radical gets that radical to go away. Right? So just like I kind of expect you guys to know what I is equal to, I expect you to know what I squared is equal to. So these are both things that you basically need to define for yourself. Okay, you should just know them. Okay. The definition of I is that it's equal to the square root of -1. The definition of I squared is that it's equal to -1. Okay. Or sorry, definition of I is equal to the square root of -1. The definition of I squared is it's equal to -1. Okay. We will need that later when we're working on stuff. Right? Complex numbers are basically real numbers and imaginary numbers combined. Okay, and when we write them, it's written in the form of A plus BI. So essentially what it is saying is that we write the real part of the number first, and then we add or subtract on the imaginary part second. Right? And so what that would mean is that 7 plus 3i is a complex number. Okay? Or -5 plus 2i is a complex number. Or 3 minus I is a complex number. Yeah. So those are all complex numbers. They're made up of an imaginary part and a real part. We always write the real part first and then the imaginary part second. Technically, all numbers are complex numbers. Okay, I can write 8 as a complex number. I would just write it as 8 plus 0i. And the same way I could write 5i as a complex number. It would just be 0 plus 5i. So technically all numbers are complex numbers. They just might not have an imaginary part, or they might not have a real part. Okay. That's not something I'm going to ask you guys to do. I'm just going to let you know that. We will be writing our answers like this later, so I just want you to be aware of that we're going to be writing our answers in complex standard form. So when I ask you to do that, it means I want your answer to look like that. Okay. So real part, imaginary part second. Anything about the complex number standard form? You guys want a question? Or move on? I hear you. Okay. So looking at example 1 here, square root of -25, and I know we talked about this yesterday, but we saw what happened earlier with the square root of -9. There is, what I would call a more complex way of dealing with this, that the square root of -25 is equal to the square root of -1 times the square root of 25, which is equal to I times 5, which is of course equal to 5i. Okay? I would just ask you guys not, I think that at this point you guys should know this well enough that you shouldn't need to do that. That what I really want you focusing on when you see a problem like this is that you see that negative and say, okay, hey, my answer is going to be imaginary, but that's not the thing I really need to worry about. Okay, it's important, but that's not what I need to be spending a lot of mental energy on. My answer is imaginary. What I really need to be worrying about is, hey, what's the square root of 25? Do I know that? Well, luckily I do know the square root of 25 is 5. Oh yeah, and I remember that I said my answer was going to be imaginary. So if you just take those two things and just combine them, you shouldn't have to tear it apart and then push it back together. You hold on to that negative and say, okay, that's giving me an imaginary number. What's this other thing giving me? That's what I really need to be focusing more on. Then I'm going to take that imaginary and then whatever I get, put them together. Okay. So when we look at something like the square root of 60, again, what I'd say I don't need to worry about. It's important, right? It needs to be part of my answer, but I don't need to be spending a lot of mental time on this, saying, okay, it's negative. That means my answer is imaginary. I'm going to hold on to that. It's right here next to on this part of my brain, just sitting there waiting for me to be done. Okay, I'm going to hold on to it. But what I really need to be focusing on is what's the square root of 60? Okay, how do I deal with that? So we say, okay, well, the square root of 60, I'm going to sock that out. So that's 2 times 30. That's 2 times 15, which is 3 times 5. Okay, so we have our sock there. Once we have it socked out, we look at for pairs. Oops. So I know pairs, that 2 times 2 is really 4. Well, that 4 gets square rooted as a 2. That pair gets to go on the outside. And then those lonely guys go back inside. And I say, oh yeah, this is supposed to be imaginary. Where does that I go? It goes there. Okay. So 2i radical 15 is the appropriate way to write that. The square root of -16 is equal to 2i radical 15. There are other ways you could write that, but I would argue that they are inappropriate. Okay, so that does mean 2 times I times the square root of 15. It's all multiplication, right? You guys should know about multiplication is that you can do it in any order you want. Okay, so technically we could say that this was equal to I to radical 15. Mathematically, that's correct. But we made, a long time ago, we said when we write letters and numbers, we're always going to put the letter after the number. We just kind of set up that rule, that convention is what it's called, right? And so that's why the I is after the 2, right? We don't write it like that. But Mr. Baker, square root of 15 is a number. You didn't write the I after that. We have another convention too, right? We don't write things after radicals because it gets really confusing about if they're under the radical or not, right? Is that I under the radical or is it not? It's hard to tell sometimes. So another rule, right? Don't do that because it's hard to see what's going on, okay? So combining those two ideas that we put letters after numbers, but we never put anything after a radical, means the letter goes after the normal number but in front of the radical. Okay? So that's why we write it this way. This is the appropriate way to write that. Okay? Mathematically, they're equal, but what's best for our eyes is this. Try not to be punny there, FYI. Okay? Anything about that you guys want to talk about? This will be the part where you guys say something so I don't feel so alone.
Can you repeat the question, Mr. Baker?
Do you guys have any questions? Was my question.
Oh.
And then I made a plea to have you guys communicate with me because nobody's saying anything. Ah, okay. See how easy that was for you guys to say something? All right, so in the WebAssign, there really weren't any problems like that, like the two we just did. The ones they had were like this, which I don't think I've ever seen problems like this before. But I wanted you guys to work with, reducing radicals. So I need to show you this so that you can deal with what's going on in WebAssign. But so they're asking us to simplify this. They'll also say something about putting your answer in complex standard form, which we already talked about. Okay. But so we got the square root of 100 minus the square root of negative 16 plus 2 times the square root of negative 9. Okay. Simplify this down. It's really pretty straightforward. Just break it into parts. Okay. Square root of 100 is 10 minus square root of negative 16. All right. Square roots of negatives are imaginary. Square root of 16 is 4. So I get 4 imaginary plus 2 times something. Square root of negative 9. Right? Square root of negatives are imaginary. Square root of 9 is 3. So I get 3 imaginary. Okay. Well, 2 times 3i is 6i. So I have 10 minus 4i plus 6i. Well, negative 4i plus 6i is 2i's. So 10 plus 2i. Does that sit okay with you guys? Okay. From what I saw, there weren't any that were you had to do like the square root of 60 or anything like that. It was all like nice, perfect squares you need to deal with. So it should be pretty easy. Adding and subtracting complex numbers should be really straightforward. It's just combining like terms. Okay, don't make it any harder than that. I definitely have seen students in the past look at these problems and multiply them, which I get, but I also would say, but there's a plus sign right there, but there's a minus sign right there, but it says add and subtract right above it. Okay, I know there's 2 sets of parentheses, visually confusing, but there are lots of other things here saying multiplication is not what you should be doing. So combine like terms, that's all it is. So 2 plus 3 is 5. Negative 4i plus 5i would be 1i. Right? But we wouldn't write 1i. We would just say 5 plus i. Okay. Subtraction, of course, same thing. Just generally people tend to make a little bit more mistakes with subtraction because of that. So a lot of times it's easier if we rewrite the problem after doing a little bit of distribution. So we have 1 minus 2i minus 9 plus I, right? Distributing that negative through, and then going and doing your like terms. So 1 minus 9 being negative 8, and negative 2i plus I being negative 1i, which again, of course, we would just say would be negative 8 minus I. Anything adding subtracting wise you guys want to talk about? Let's take a roll here real quick. Let's see, multiplying. I did want to do this problem first. We're getting the other one, so kind of called this example 3 instead. I'm not going to do all the I to different powers stuff. So 9i times 5 minus 3i. That's hard. All this is just a distribution problem. Okay, so 9i times 5 would be 45i, right? Just like 9x times 5. And that same way, 9i times negative 3i. So if we said 9x times negative 3x, well, 9 times negative 3 is negative 27. And x times x is x squared. Well, I times I would be I squared. Then but what's I squared equal to? Yep, negative 1. So we have a simpler way of writing this, right? 27i squared. So what you guys will see me do is I'll circle this thing. Like I know I need to simplify this. I like to circle it and kind of kick myself off to the side. Hey, negative 27 times I squared. That's the same thing as negative 27 times negative 1. Well, negative 27 times negative 1 is positive 27. I always write the plus sign there. I really want to emphasize to myself that it's positive 27 now. Because then when I kick it back over here, it's now a plus 27. Okay. Well, that's not in standard form, right? Because it's not the right order. So 27 plus 45i. So when working with I, you do not leave any higher power i's in a problem, okay? Whether it's I squared or I cubed or I to the 12th, like you would always simplify that down. We won't be working with any I cubes, I to the 4th, I to the 12th. Right? We're gonna top out at I squared, but the idea is that you would always simplify that down if you had something higher than just an I. Okay? Anything there you guys want to pick at? Okay. So let's move over to number 4 here. And just another distribution problem, right? Just kind of more of a FOIL problem. So 2 times 4, of course, is 8. 2 times 2i would be 4i. Negative 3i times 4 would be negative 12i. And then negative 3i times 2i would be negative 6i squared. Okay, what you're going to see me do with something like this is just kind of highlight this to myself. Hey, I squared, I can do something with that. Right? And then I start thinking, what's negative 6 times I squared? What's negative 6 times negative 1? That's really positive 6. So I circle it, I write what it's actually equal to, like right next to it, right below it, and then I cross it out. Okay, I've dealt with it, I've simplified it. Here's what it's actually equal to. Okay, I don't want to have to rewrite the whole thing again because I had to rewrite the whole problem and then do some more work to rewrite the whole problem. So this is just a kind of a shorthand way of noticing it, dealing with it, and then getting rid of the old one. So, okay. If you see somebody else do this, they may do it a completely different way, but that's purely just like a notation thing. Okay, the math is going to stay the same. It's kind of like I have my own way of kind of writing the AC method stuff. That's the same idea that anybody else would use. 8 plus 6, 14. 4i minus 12i, negative 8i. So distribute, deal with your I squared, combine like terms. Shouldn't be too big of a deal. Adding, subtracting, multiplying, dividing. Sorry, adding, subtracting, multiplying with i's shouldn't be a big deal. Okay. Division's its own little kind of nasty thing, but that's often the case for division. So. You guys feel good about all the other operations, the first three? Again, this is all stuff you guys have done before, but wouldn't expect that you guys particularly remember this, especially the division part. In order for us to do division, we need to define something first. And normally when we teach this for the first time, if we had more time here to deal with this, I would have done it the same way. But with you guys, even though we're kind of reteaching, is that we explore foiling stuff quite a bit. And we give you a couple problems of those, and then I would throw one at you that's kind of special, right? I'd say something like, 2 minus 3i times 2 plus 3i, and see that. And then I'd do another one that's kind of similar to that, and start noticing that there's a pattern, that when the two expressions have a pattern to them, then the answer turns out to be kind of special. And so then we say, oh, well, let's define that. Let's give that a name. Okay. And that name of that special relationship is conjugate. Okay. So the conjugate of 3i, and the way I'm going to define it is basically just kind of give you an example of it, and it's usually enough to make sense of it. So the conjugate of 3 minus 5i is 3 plus 5i. Okay. The conjugate of negative 7 plus 2i is negative 7 minus 2i. The conjugate of 8 minus I is 8 plus I. Okay. So hopefully it's pretty easy to tell what conjugates are, right? The only thing that changes is the middle sign. Okay, that's what it means to be a conjugate. And I'm going to very briefly explain what would happen if we took 3 minus 5i times 3 plus 5i. We go through all the foiling, combining like terms, and all that stuff. We would end up with 34. Okay, so by multiplying those two things, we don't have any i's in our answer. Because of the way they're formed, the i's get canceled. Notice here we multiplied two binomials. They both had an I in them. We still had an I in our answer. Multiplied a binomial times a monomial. They both had an I in them. We still had an I in our answer. Right? So that just multiplying by I wasn't enough to get rid of the I. Right? There had to be something else going on there. So it's all about that sign switch. And it's very similar to the difference of squares stuff that we've seen over and over again. Okay? But by multiplying something by its conjugate, multiplying a complex number by its conjugate, we actually get the imaginary parts to cancel. We're left with just the real part. Okay? So we want to take advantage of that when we talk about division. Okay? And why that's important with division, follow me down this road a little bit. Okay? Division is a grouping idea. Okay? So if I say, hey, there's 10 of us, let's get into groups of 2. You guys know, roundabout way, that means there's going to be 5 groups, right? Or, hey, there's 10 of us, let's get into groups of 5. We know in a roundabout way that means there's going to be two groups, right? Grouping or division is a grouping idea, either how big are the groups or how many groups are there. If I say it's divided by 2, do you want to be in 2 groups or do you want to be groups of 2, right? It could be either. We need to know how big the groups are in order to make sense of division. How do I divide something by an imaginary sized group? Hey, let's get into groups of 2i. How do we do that? Right? It's almost like me asking you guys, hey, there's 10 of us, let's get into groups of 0. Right? Well, turns out we can't make sense of that. It turns out it's impossible to get groups of 0. Okay? So we call that undefined. Right? So if we're unable to divide by imaginary numbers, we can't get into groups of imaginary size, then doing a problem like B here would be impossible unless we had a different way of thinking about it. Okay? What we want to do is take that denominator, that thing we're dividing by, our group size, and change it so it's a real number only. So when we do this problem, our whole goal is just to take the denominator and get it to be a real number. Our answer is not going to be something that we're really going to be able to make sense of. Just like on the last problem, our answer is not really anything we can make sense of. 2 minus 3i times 4 plus 2i is equal to 14 minus 8i. I think it's 14 minus 8i. I don't know, right? It's nothing we can really make a concept of, but we can understand how the math works. Okay, I multiplied these things, I combined these things. I can see how it got there. Okay, so in the end with B here, we're just going to end up with something kind of like 14 minus 8i, where it's going to be a mess of i's. But our main goal is to make the denominator something that we understand better. What is my group size actually? How do I divide by this thing? Oh, I know how to divide by 2. I have no idea how to divide by 2i. So can we make it a 2 instead of a 2i? Kind of that idea. Okay? So our goal here is to change the denominator and not necessarily get a number that we can make sense of. Okay? So from what I just explained to you about conjugates, if I want the I to go away, then I need to multiply that 3 plus 2i by its conjugate. The conjugate of 3 plus 2i is 3 minus 2i. When we do that foiling, the I part, the imaginary part, will go away. And we'll see how that works here in a second. But remember, whatever we do to the bottom of a fraction, we have to do to the top of a fraction or else our balance gets lost. So if I do that to the bottom, I also have to do that to the top. Right? And that this does keep balance because 3 minus 2i divided by 3 minus 2i really equals 1. Right? So we're just multiplying our problem by 1. So the value doesn't change. Right? That wasn't our goal, not to change its value. Our goal is to change the way it looks, to get the I out of the denominator. Okay? So we're multiplying by 1, but with the goal of just changing the way it looks. So we got a couple FOIL problems to do here. So I got 2 times 3 and 2 times negative 2i. So I get 6 minus 4i on the top. 5i times 3, 5i times negative 2i, which would be plus 15i, negative 10i squared. I'll come back for that I squared later. 3 times 3, 3 times negative 2i, two I times 3, 2i times negative 2i, so plus 6i minus 4i squared. So like I said, we'll come back for that I squared later. So negative 10 times 2i squared, negative 10 times I squared is equal to negative 10 times negative 1, which is really equal to positive 10. Right there, get rid of that. Negative 4i squared, negative 4 times negative 1, which is equal to positive 4. Again, I'm always going to write that plus sign. I really want to emphasize myself that it's a plus. Okay, so I'm going to write the plus. Okay. And then we have some like terms, right? So 6 plus 10 is 16. Negative 4i plus 15i is 11i. 9 plus 4 is 13. Negative 6i plus 6i is 0i. But I wouldn't write 0i, that's silly. So think about our goal, right? Get the I out of the denominator, make sense of our group size. What are we dividing by? How big of groups do we want? How many groups do we want? Right? I want group size 13, or I want 13 groups. I know how to make sense of that. I may not know how to divide 16 plus 11i by 13, but I know what it means to divide by 13. So I've made more sense of the problem than where we started. Okay? I had no idea how to divide by 3 plus 2i, but I know how to divide by 13. Okay? The last thing we should be checking is if this problem can be reduced, right? As a fraction, can you reduce your fraction? Okay. 16 plus 11i divided by 13. Those don't share anything, right? So there's nothing reduced there. So we're done. Okay. What if what if you ended up there, right? Negative 7 plus 14i equals over 21. Oh, those all have 7 in them. That's negative 1 plus 2i over 3. Yeah, I can reduce that. All right, they all have a 7. Yeah. What if it's negative 7 plus 15i over 21? Ooh, negative 7 and 21, they both have a 7 in them, so that should be equal to negative 1 plus 15i over 3. No, please don't. Okay. Right, they all need to share something in order for it to reduce. They all have a 7 in them, take it out. These do not all have a 7. These do not all have a 3. I can't take that stuff out. Okay? 16, 11, and 13 don't share anything. No reducing. Okay? You can't reduce part of a fraction. You have to be able to reduce the whole fraction. Okay. Sometimes we have no idea what to do because we don't know what we're trying to do. Right? With this, we see divide. Right? We're really not trying to divide it. We're just trying to simplify the fraction, essentially. Get the I out of the denominator. Okay? Because we can't actually do the division. So we can just simplify the way it looks to us, though. Okay. Anything about that one? It's pretty tricky. You've got to remember to switch the sign. It's the only way to make that work. Okay? It's the only way to make this go away. How's that feel, Wesley? How's that feel, Marlo? Katie? Ah, the crushing weight of how alone I truly am. Oh, hey, Marlo. Okay. All right. Last one. I'm going to show you guys 2 different ways of doing this. The first one I'm going to show you is probably what I see most students do come test time, and which I would argue is not the... 1 is never the way I teach them to do it. 2 is not what I would consider to be the easiest way of doing it. So, but I'll show it to you just so see how it feels. So if we think about what we just did, right? We want to get our goal is no different. We want to get the I out of the denominator. I don't know how to divide by negative 5i, but I do know how to divide by negative 5 or 5 or something like that. Like if it was just a normal number, I could figure out how to make sense of that. Okay, let's get the I out of the denominator. We saw that to do that, we would need to multiply by the conjugate. That allowed us to get rid of the I. Okay, so if we think about what would the conjugate of negative 5i be? Well, remember, all numbers can be written as complex numbers. So this is technically 0 minus 5i. Well, that would mean that the conjugate would be 0 plus 5i, right? Well, why would I say 0 plus 5i or anything, right? That's silly to say, right? I don't need to say that, but that's how it would. So really what we're just going to multiply by is 5i, right? I need to change the sign, right? That was the goal, right? Or that was what really happened, right? Was just change the sign, right? And that was enough to deal with it. Well, if I multiply the bottom by 5i, gotta do that at the same top, right? So where does that get us, right? So 4 times 5i, and then 5i times negative 3i. So that would be 20i minus 15i squared. We'll be back for him later, right? And then negative 5i times positive 5i would be negative 25i squared. Well, we always deal with I squareds, right? Simplify them. Negative 15i squared, well, that's really equal to positive 15. Negative 25i squared, that's really equal to positive 25. So where does that give me? 20i plus 15 over 25. Well, this is out of order, right? That shouldn't be written like that. So those need to be switched, right? We also notice that everything has a 5 in it. So what's that really equal to? Well, 15 divided by 5 is 3. 20i divided by 5 is 4i. And 25 divided by 5 is 5. So 3 plus 4i divided by 5. All right, did we get our goal? Right? Is the I out of the denominator? Yeah. Okay. I know how to divide by 5. Anything about that feel weird? Okay. So remember, I don't think that's the easiest way to do it. Really not too much that we did there, right? But I don't think that's the easiest way to do that. If you look at the last step and think about what we did, right? Our last step was to take 5 out of everything. Why did we have to take 5 out of everything? Where did that 5 come from? Well, that 5 came from us putting 5 into the problem, right? We multiplied everything by 5 in the first step. Why did we multiply everything by 5 in the first step, only to 2 steps later take it right back out? What was the point of multiplying by 5 just to take it out 2 steps later? Did it do anything? Did the 5 help you get rid of the I? I would say no. You don't need to multiply by 5i. You just need to multiply by I. The I is what got rid of the I. The 5 didn't help us. Okay. So I do that on the top. 4 times I is 4i. Negative 3i times I is negative 3i squared. Negative 5i times I is negative 5i squared. Negative 3i squared is equal to positive 3. Negative 5i squared is equal to positive 5. This gives me 4i plus 3 over 5, which of course I wrote out of order, but we can see that those are the same. Okay. Why did we multiply by 5 to take, just to take it out later? It made no sense. Okay. With a simple denominator like this, with a monomial denominator like that, all you have to do is multiply by I. Okay? There's a shorter way. It's just like saying, hey, easy AC, right? Shortcut AC. If A is 1, let's do it this way instead. It's faster. We could leave out all that middle junk. Or, hey, look, it's a difference of squares problem. I could technically do that with AC method, but I know a lot faster way because if the problem looks like this, I can do it like this instead. Same thing. If the problem has a monomial denominator, right? There's no real part here. It's just the imaginary part. All I have to do is multiply by I. That's enough. Okay? It's not that much more work to go this way. Right? And it worked. Worked fine. But it is more work. Why are you putting a 5 in just to take it out later? What did it do? Okay? I would suggest you do it this way, guys. Okay? So a couple choices there on A. You have to do B like this. There's no other way to do that. You have to multiply by the conjugate in order to do that. Okay? So you kind of got to weigh that out against yourself, right? Do I want to learn 2 different methods to save some time on one type of problem? Or I just want to learn one method where I'm always changing the sign, right? That is, I guess, kind of the benefit of that. It's not that much more work to do it. You're not saving yourself that much time by dropping that number off, and you don't have maybe to memorize another different way or a trick for a certain type of problem. I get that. But it is less work, so I'll leave that up to you guys to figure out what you want to do for yourself there. Okay.